Hi everyone, so let's get started with lecture 4. So in this lecture we're going to look into the implementation aspects associated with the simplex method. So we're going to first discuss basically the key features on an algorithmic standpoint in terms of changing bases and selecting what are the elements that are going to compose the next bases. And then in the second part, we'll talk about algorithmic choices within the implementation of the simplex method. So we're going to discuss ways of making it more efficient and a little bit of the Tableau representation, which is something that is often used when you're discussing aspects of the algorithm itself. And then we'll finalize giving a geometrical insight related to the fact that why is it so that even though the worst case scenario for the simplex method being having to go to every single vertex until deciding which is the optimal, we can see that actually the number of steps is usually much smaller than that. So that is to give a geometrical intuition on why is it so. All right, so let's get started with this first part. So just to recap, we're talking about problems in Rn, and like so, my vector C is in Rn as well. Our matrix of m constraints and n variables. And this is the set of all variables we're considering. And we have this LP in its standard form with only equality constraints that is written like so. And we've seen that employing the simplex method to solve P is basically starting from a non-degenerate basic feasible solution. So the premise is that we have an initial basic feasible solution to start from. This is an important thing that we're going to come back to in this class later. So from this basic feasible solution, we look at the set of reduced costs and pick a negative one. We seen last class that a negative reduced cost means that that direction has the potential of improving the objective function by making it smaller. So we're using this standard of minimization, and that's why we're talking about negative reduced costs. If you're thinking about maximization problems, instead, then this you just have to switch this to a positive reduced cost, right? If all of them are greater and equal than 0, we saw at the end of last class that that's a condition for optimality, so you just return the current solution you have because that solution is optimal. However, if it's not the case, then we define a direction D to move along. We saw how to define that direction. It's based formed by this basic part and this non-basic part. The non-basic part is basically defined as being 1 for the direction you want to go, associated with that variable j, and all the other non-basic directions set to 0. And then you calculate what is the change in the basic variables given that change in the non-basic variables. And we saw that we get, in order to calculate that, we get this vector given by minus b, minus inverse of b times the column in A associated with that non-basic variable you're turning into basic. And the algorithm is just a rinse and repeat of these 3 steps. Some aspects we have to look into is first is that when you're moving along this direction D, in by a step size theta, of course theta has to be greater than 0, so you actually move. It makes my non-basic variable that was previously 0 take a value that is strictly greater than 0, so we say that it enters the basis. And meanwhile, it reduces the objective value at this rate. And we also saw that last time. So that's kind of just to put us on the footing, on the right footing, so we can start what we have to talk about the simplex method. And of course, once we decide that that's the direction we want to go, and that direction is known to give us improvement, what we want is that to move as furthest as possible. So find this maximal theta bar that will occur on this change in the objective function. So we know that in that direction, going in that direction gives a change of this rate, and we want to impose in the objective function as much change as we can. which implies that we will be looking at a change that looks like so. The question is how we define this theta bar that works as we're expecting. And so let's talk a little bit about that. What is constraining you in terms of moving along the direction D? You know that the direction D is going to give you improvement in the objective function. So what is constraining you in terms of moving in that direction is basically feasibility. Feasibility is the main issue here. You can't carry on going in that direction all the way, because eventually that is going to cause you to leave the feasible region, right? Remember that when it's aching to do this. So suppose we are at a vertex here, and we somehow know that going, say, in this direction is the direction where I improve my objective function. So the direction vector D in this space is pointing towards this. So ideally, if I could, I would like to go this towards infinity and beyond, because this is going towards where in a direction in which I know my objective function is improving. Why I can't do that? Well, I can't do that because if I carry on going further than this point there, what is going to happen is that I'm going to leave my feasible region, which is described like so. So I have to make sure my step size is such that it takes me only to here. Otherwise, I'll leave. So, and how do I identify this effect? Well, we'll look at the variable that is associated with this constraint in the standard form and make sure it doesn't become negative. So it doesn't cross the variable associated with this constraint is positive here. It becomes 0 at exactly this point when this becomes active. And then it's going to become negative if I carry on going in that direction. So that's what I want to prevent. So to do so, what I have to do is to make sure my theta is the maximum value of theta greater or equal than 0. This is normally theta it would be exclusively greater than 0, but in some cases in we have degeneracy, this actually sometimes might have to be 0. We're gonna see something like related to that in a few minutes. It's still in this part of the lecture. So, but basically we're looking for the theta such that when I move theta in that direction D, I still observe feasibility. And observing feasibility means satisfying this and satisfying this. So it's the condition on x greater than or equal to 0 and a condition on ax equals b. All right? But by construction, we can see that this is going to be the case because we have that AD is 0. So when we define the direction, remember last class when we were defining the vectors dB, we did it so that this condition is observed. That is actually how you derive the B inverse of B times AJ. So if that is the case, it means that this term, because this is going to disappear, it's going to still be AX equals B. So basically is that D is defined in a way that you're always walking on the lines that form the boundary of the polyhedral set. So this is given. We don't have to worry about that. What we do have to worry, though, is that sometimes we cross lines, like in the picture I just drew. So you have to make sure is that this condition, the condition that guarantees that when you're moving, no variable is turning negative. They're all turning either 0, those that are becoming no basic, or just simply changing in value. Okay? So basically what you have to do is that whenever you set your theta, your step size, it has to be in a way that is the minimum among all the possible steps you can take, right? So it's almost like looking at each direction and see, well, if I consider this variable specifically, I can only walk, say 4 steps. And then there is this other variable that tells me I can only do 3 steps. So if I decide taking 4 steps, I'm going to break the condition that told me beforehand that I could only take 3 steps. So in order to make sure I have a step size that is good for all directions, I have to pick the minimum of them, because in that direction where 4 steps is good, 3 steps also are, right? So that's exactly what's going on. For all basic variables in the set of basic indices, for which D is strictly negative, notice that you don't have to worry if your component D is positive, because because this is assumed to be positive as well, if this component is positive in your direction vector d, there is no way you can make a variable negative. You can only make it negative if it points if this component is less than 0. Okay, so yeah, so basically for those specifically, we enforce that this condition must hold for all the i's that are basic, for which d is a negative. And just doing some rearranging, moving the x there, dividing by the component di, I get something like this. So theta bar is less than minus xi over di for all I in B. And that's exactly the equivalent. If something, it must be that something's less or equal than 4 and something is less or equal than 2. Then to satisfy both, it had less or equal than 2. So this is exactly that. This is the same as saying that instead of this holding for all I in IB is the same as looking at the minimum for which these are negative. And this is something that you see if you have done introduction to optimization as the quotient rule, because it's basically dividing xb by its term db and picking the smallest. So like we said, for d greater than 0, you don't have to worry because there's no way you can make this negative with positive values of theta. And in case of non-degeneracy, then there is trouble. No, there is no trouble because this is always strictly greater than 0, meaning that your theta is always greater than 0. The problem is you have trouble with degeneracies because this sometimes might be so that if your basic variable is 0 and that's the condition for degeneracy, then you might get stuck because your step size becomes 0. Okay, right. So here is an example from last class. We looked into this when we were calculating reduced costs. And so now what I'm going to do, instead of having the C's, so you can see where the numbers are going, I'm actually going to give a number. So that objective function is actually minimize 2x1, and this is all 0, right? And let's assume I start with a basis 1, 2. So I have this basis that has my matrix B is 1, 1, 2, 0. Notice that this is x3. And then when I solve that system like so, I can see that x1 and x2 equals 1, right? So I have x1 plus x2 equals 2, and 2x1 equals 2. So from this, I get x1 equals 1, and from when I plug here, I get x2 equals 1. This is how we calculated before. We calculated the reduced cost for C bar 3. So we saw that it looks like this. So when I'm substituting 2, 0 here, basically what we're getting is this minus 3. That is coming from the multiplication of this by 2. C1 is 2 times this gives me minus 3. So the reason why I want to show this is, suppose now we want to see how much we can increase x3. We just decided that x3 is going to be the variable becoming basic, so we have to decide what variable is going to come out. But in this case, because remember that this is my vector d, my vector d in this case is this is minus 3, 2, and 1, 2, my basic directions for variables 1 and 2. Variable 3 becomes basic, and variable 4 is non-basic. And because this is the only negative term, only x1 is something that I have to worry because the value is going to decrease when I make x3 bigger. So the value, largest value here, I don't have any minimums because I have only one component, but it's basically the division of x1 by g1, which is this term, and I get exactly 2/3. So what happens is my next point that I'm going, which is x, remember that x we just calculated, that was 1000, sorry, 1100. This is the basic part, and this is the non-basic. The other two is the non-basic variables. So this plus the step size 2/3 I just calculated, plus my d vector, which is exactly this vector here, gives me this new point. And notice that in this new point, now x1 is 0 because x1 is non-basic, and x3 is 2/3, which is exactly this value of the theta dam. So I just did a base swap, and in this new case, my IB, my indice of basic variables, is now 3 and 2. It doesn't matter the order, I'm just emphasizing that this became what was 1 before. Okay, so that's the mechanics behind it. Right, so just a few quick remarks is that your new basic variable that was non-basic before, it takes exactly the value of theta, because for that component, d is 1. So, and the x was 0 before because it was non-basic. And then this here is just, making sure that we realize that the previous basic variable becomes non-basic, and like so automatically becomes 0 as well. So L is the coefficient of the basic variable that left the basis. So I like to use this L because it makes a reference to leaving. So BL, it was in the basis, but then left. Okay? Yeah, and that's not hard to see. Basically, because of the way we defined what theta would be, if this is the fact, the one leaving, then D is precisely this, and you can cancel out that component with that, and you get xbl minus xbl, right? So this is the value of theta. And because of that, the basic variable becomes 0. Because the former basic variable becomes 0. And the method is built like so. So you just did a swap. And if you remember the discussion we had last week about adjacent bases, this is exactly a adjacent basis, right? I hope it's clear to you now that what we're doing is creating this new basis B bar, where everything else is the same in terms of basic variables, with exception of that L that left, that basic variable L, the index L that left. And that element bi, that for each I equals j, is who became the new, for each I equals L is the new basis. So basically what happened was this. My original matrix had a, let me do it like so, had a column here instead of this column. So this is B bar, and for B, it was exactly the same thing, but then this column there was A, B, L. And exactly the same thing here as well. So this got removed and became that column there. So that was the swap we did. So, and we defined last time that the adjacent bases are bases that they share everything but one column. And that's exactly with that. So we went to a point to which we are connected through a line segment. And this is just the, so this is the result, a technical result, showing that when we do so, when we move to an adjacent basis, doing as we did, this new basis is a basic feasible solution. Well, it is a basis, a valid basis, B bar, with which you have this solution associated to. And that's basically what the theorem is trying to say. Okay, so proving that I have the proof here for us to go through together, because it has some interesting aspects to it. But it has a kind of a interesting trick that you're going to be using you might want to use as well when you're looking at your own exercises. So let's prove that by contradiction. So basically what I will do, I will assume that they are not linear independent. And that is the condition that I need for this to be an actual basis. Okay? And notice what I'm doing is that I am saying that my columns of my previous basis minus the column I just removed, and I'm comparing that with the column I want to make into the basis, including the basis to make B bar, they are not linearly independent. Okay, so if they're not linearly independent, that means that I can find a collection of multipliers for which, when I do so, I observe this. I can make them 0, right? And if it is the case with this matrix, it will also be the case if I pre-multiply this by b minus 1. This might take a while for some of you to convince yourselves, because I think that the easiest way to see how is it going is that you know already that B is it's a matrix of linearly independent vectors, columns, right? So and so it's inverse, and by doing so, when you pre-multiply a matrix by a matrix with linearly independent rows, what you're doing is just doing a linear scaling of that matrix. So think of this matrix with columns being vectors. What you're doing with these columns is basically perhaps changing the angles and changing how long they are. But you're not making any of them disappear or have components that become 0 specifically. So by doing so, you still, if this is true, this linear transformation of A will still have their linear dependence that originally had. You can't make A become linearly independent, have linearly independent rows by doing so. Um, so that then is the case, and we know that when you look at this matrix with the new basis and you think about that matrix with the old basis, you can see that for all columns with exception of that L, this thing is the unit vector EI. And remember that this vector EI is such that it's zeros all over with exception of the entry I that has a value 1. So if this is E3, so it's a vector that has 0, 0, 1, and then 0 everywhere else. So basically, for this, many of these columns are the same of those, with exception of 1, right? So when you do this, for all the other basic columns, the columns of the basic matrix B, you're going to get this vector. And therefore, that L component is going to be 0, right? It's we'll have a graphic representation of that, but basically for every all the other components, you'll have either zeros or ones, but because you don't have the column EL, EL is absent. So for that one, everyone else will have 0 in their L component. So that is important for us because we know that now when we look at the vector b minus 1aj, the vector b minus 1aj is such that that very component bl is by definition not 0, because when we calculated d, we did it so in a way that d wouldn't be 0 for that component. Remember that we just selected theta, taking into account this. We only look at the strictly negative, so we don't take 0 values. So we know that this component will be different than 0 for that alpha row of the matrix. So this is by definition, because it has a component different than 0, where everyone else has a component 0, all the other columns have a component 0, then it will be linearly independent from this matrix, which is exactly this matrix. So when I make the matrix when I make the matrix B, so notice that this is identical to B bar. Yeah, the columns of A in the basis, the new basis. So that is going to be the previous vectors and AJ, which I just showed. I just showed that b minus 1a is independent of b minus 1j. So just the same argument that it holds for here. So the columns of my original matrix plus combined with that column of j is also gonna be linearly independent, and that's kind of a long way around, but this shows because this is gonna be a contradiction because I assumed that they were not linearly independent, so it must be that they are linearly independent, and that's about it. The last thing to show is number 2 there, which is showing that this is a basic feasible solution. Well, we just showed that B bar is a basis. So the last thing to show is the feasible part. And to show the feasible part is just by construction. We're just seeing that this condition is satisfied by construction. This condition is satisfied by construction. So this is obviously feasible, and we know that it's basic as well. So it's basic feasible solution, and that's all you need to finish the proof. And once we know all that, I think we have everything. I'm sure now we have everything that we need to pose the simplex method as an algorithm. So here is what we call a pseudocode, which is an algorithmic representation of it's how you would implement the method given some poetical license to write things that you wouldn't need, that you couldn't with code. So we use like words, but you try to replicate what would be the structure of the algorithm. So here is a pseudocode summarizing the simplex method. So we start with a basis B, and with that we have an associated basic feasible solution, and we have pre-calculated the reduced costs for that basis. And while you still see reduced costs that are negative, that means there are potential for improvement. So what you do is you pick a j for which you observe this component being negative, and then you calculate this auxiliary vector that I'm calling u, which is basically the inverse Baj part. The reason why we're exposing this like so is just that because that it makes clear that we actually have to solve a system here. You can calculate this u using backslash operator. And if you find out that the whole vector u is negative, well, remember that this is almost the vector db with minus the minus in front of it. So having all the vector, all u, all zero or negative component-wise, means that all the directions are either 0 or greater than 0. And remember that this test that we did before only chose those that are strictly less, right? The reason for that is basically if you have this happening of all your d's are greater than 0, it means that your problem is not limited in growth. Well, in reduction of the objective function. So you can carry on direction d forever. And if you can carry on direction d forever, it means that your problem is unbounded. So you get like a minus infinity value. We'll go back to this in a second. Otherwise, your step size is set like we just seen before. Notice that I'm removing the minus here because I'm using the u directly. It's just for an algorithm standpoint. And then what you do, you can directly send your xj to that data you found, and your new basic variables, the remaining basic variables become this. And we saw that by doing so, the old basic variable that became non-basic will automatically be set to 0 as it should. So you form this new basis. Remember this is an overload notation, so I'm actually switching the column in the matrix B and switching the index in my list of basic indices. And then I calculate my reduced cost for my new basis, and what it takes me is to this check again. And if this time I don't have any negative reduced cost, then I'll return my optimal basis and my optimal solution. Normally I just need a solution, but it's good practice to return the basis, because then you can calculate objective costs. You can calculate, you'll see later on, we'll talk about shadow prices and things like that you can calculate as well outside the algorithm. And this is just it's a theorem to show formally the convergence of the simplex method like we just seen. And it actually is one of these theorems that you can just argument by logic. And it goes like so. So suppose you have P that has at least one feasible solution, and that all basic feasible solutions are non-degenerate. So you trying to find at least one. So it has at least one feasible solution. So I can start with something, and that all of them, if you have only one, that unique one, but otherwise all of the basic feasible solutions are non-degenerate. Then the simplex method terminates after a finite number of iterations. It might be a large number, but it's finite. So it stops before the end of the times. So it either returns a basis B and the associated BFS that are optimal, or D such that all the components are non-negative. All the components are non-negative, so they are zero positive, and that makes the problem, and that makes it so that my optimal value becomes minus infinity. So that was the case of that if that we were testing in the algorithm. And that goes like this. So if that condition in line 3, let me go back so you see what condition is the condition whether I have negative reduced costs. So so if they are not met, then the basis and associated basic feasible solution are optimal. In that we saw that in theorem 9 of the last lecture, which is the optimality conditions theorem. Otherwise, what you do is the line 5 condition is met. Line 5 condition, line 4 condition is met. And then D will be such that this is the case, but the other components are greater than or equal than 0. So that will imply that you cannot make any solution non-feasible, infeasible, by increasing this. So if this is the case for all theta, then that is going to be the case for this when this goes to infinity. And that going to infinity causes a value reduction, making this go to minus infinity. So it's basically there's no limitation on how much you can improve the objective function. Now, if you have then step sizes that are strictly greater than 0, are taken along D, and they satisfy this. I mean, in the normal situation where you have negative components, because this is the case, whenever you form your vector D, once you moved towards the direction, it's gonna be such that your reduced cost will be telling you something on the lines that if you go back the direction you just came, you'll make the objective function worse by the same amount you just improved. So if you think about if you were at point X and you went to point Y, this had a Cj that was negative and telling you that you would improve your objective function by proportionally to this component of the reduced cost. If you consider coming back the next iteration, this reduced cost will have flipped sign because you will make the objective function worse. And because of this way that you do, always picking the next negative reduced cost, otherwise you exit the algorithm, it means that you never this is the variation you impose in the objective function is always decreasing. It's monotonically decreasing. It's non-increasing or strictly decreasing. So basic feasible solutions are never visited twice. So you keep moving from improving to improving basic feasible solution until you stop. You never come back in the non-degenerate case. And because we've seen there is a finite number of them, combinations of the number of constraints taken the number of elements you need crossing to form a vertex, then this thing will eventually terminate. And that's what we need. And that proves that the simplex method converges. One thing that you might be asking yourself is, okay, but we keep saying that, excluding the degenerate case, but what if there is degeneracy? And degeneracy is something that happens in reality and very, very often, to be honest. So how do we deal with it? Well, the answer is there are different ways of doing so, and to be honest, it's mostly an algorithmic standpoint. It's a computational solution rather than a theoretical solution. But it is an important pitfall for your method, for the simplex method. It can make it break, because once the current BFS is degenerate, it might be so that you start to having these step size zeros. So you stuck at the place you are. You're giving a step in that direction, but your step is of zero size, and that's a problem. It means that you're not moving anywhere. So you're defining a new basis. You're doing the swap between one non-basic variable becoming basic and one basic variable becoming non-basic. So you're doing everything you should be doing, but the basis change. Yet the let's call the geographical position doesn't. You're still at the same place. Is that story that you have a vertex that is formed by two more than in R2 that is more than two constraints, and you're just swapping those that are active, but they represent the same point. So we're not moving, and that's what is called cycling. And sometimes you might see we call it stalling, like in airplanes. They stall when they lose air resistance, so they fall down. And it might be so that it might be that when you actually do a step, you might enter a land of more than one basic variable becoming zero, and that's when you're making the solution the degenerate. So basically, there is a situation where you are at a degenerate solution, and that might happen, or there might be the situation where you move towards a degenerate solution, and that we actually seen this before. Is when you get into a solution where your basic variable is zero. So here is a picture, more or less illustrating this effect. So basically, we are assume that we are at this point here, x. Okay, and this is that representation where we have a variable for a select variable for each of the constraints, and this point is degenerate because it has 1, 2, 3, 4 constraints defining it in R2. So my basis is formed by two variables, and whenever I make whenever I make two variables zero, I find a vertex. And suppose that this is the case that 4 and 5 are set to non-basic variables, forming the zero that gives me this. Because 4 and 5 are my non-basic variables, I have two options. Either make 5 basic, moving in this direction, so 5 gets greater than 0, so I'm moving inside the constraint defined by it, or 4 becomes greater than 0 and I move in that direction. So I'm either moving direction F or G. And both are infeasible, as you can see. This is infeasible and this is infeasible. So that would be the case where I get a theta that is 0. So I actually, suppose I make 4, I decide to make 4 a basic variable. So that means that I can't move in this direction at all. So my step size is 0. I stay here still. But that is done so by making, say, x2 non-basic, which now this point becomes represented by the intersection of this constraint and this constraint. Now, in that case, now becomes the following. I have two options. I can make x1 non-basic and go in this direction, or I can make, again, x2 basic and go in this I can go in the direction of making x4 basic, or I can go in this direction of making x2 basic. Yeah, because x2 is positive on this side. Clearly, this is an infeasible direction, so I go towards this direction instead. And then that would take me to the point Y. So 2 iterations it was taken, and eventually it just stalled, but then it found its way and went to Y. But it could be so that, we could be cycling among options here that keeps taking us, giving only infeasible direction options, and we keep having 0 step size, and the algorithm keeps cycling in this black hole of a degenerate vertex. So this is an example of the issue with degeneracy. So that's it. Let's stop here, and then we'll carry on talking about implementation details of the simplex method. So see you in the next video.